So here comes a great question from Chapter 7, Section 2, where we are learning to create confidence intervals for means. And the trick with this section is that there are two different ways to do it. One way uses the student's t distribution, and one uses the normal distribution. And it's a thinking class, not a math class, so we have to decide which one is the appropriate one to work. The facts they give us, besides the fact that here are all these values, is that the confidence level is 99% for no good reason. Why don't they use 95? They tell us that sigma is not known, and these are a histogram of players' salaries of football players on a team, 59 of them. So sigma is not known. If we look at the book on page 326, at the end of Chapter 7, Section 2, they give us a nice little table for how to choose. And the sigma not known always uses student t distribution. So that's what we'll use here, student t. Why would we have possibly chosen neither one applies? We would say neither one applies if we fail to meet our requirements. What are the two requirements? The two requirements are that it has to be a simple random sample, and I guess it is because I'm assuming. And the other reason would be that sample size has to be greater than 30, and we have 59 players. And so that's okay. So the t distribution will work for us. We just have to find what the value is. So in StatCrunch, we go to stat, we go to calculators, we go to the t calculator. There were 59 players. So using our formula n-1 to get degrees of freedom, we say 59 minus 1 is 58. I'm going to take the shortcut and use the between tool. We have a 99% confidence level. So change this probability, this area, into 99. And my right-hand side will have 2.6633. I'll round that to 2 decimal places and get 2.66. That's how to do it. Here's a very typical example of a question where they try to trick you, and sometimes they're successful, so be very careful. This is Chapter 7, Section 2. We are dealing with confidence intervals for means, and they have a data set that they've provided us with. There are 103 different body temperatures of healthy adult humans, and the mean temperature was found to be 98.3, and the standard deviation was found to be 0.73. And they want a 99% confidence interval estimate of the mean body temperature of all healthy humans. In other words, they've given us X bar, 98.3, and they want the confidence interval for mu, the population mean. The way we would do this is we would look on page 236 of the textbook at this little table, and they say if sigma is known, and look at this question, it says the standard deviation is 0.73. The problem with this is this standard deviation is the standard deviation of the sample of 103 body temperatures. We do not know sigma, we only know S. So we do not know sigma, so we are using student's t distribution. They give us tables if we want to use them, and we don't want to use them because we have nice tools built into StatCrunch. We go to stat. We go to t stats because we've just determined we need to use t because we don't know the standard deviation of the population, sigma. There's only one sample with a summary. The sample mean they gave us was 98.3. The sample standard deviation was 0.73. And the sample size was 103. StatCrunch in the background will do the dirty work of subtracting 1 and calculating our degrees of freedom. They want a 99% confidence interval. Again, for no good reason, they're randomly choosing these things. I encourage you not to treat statistics in such a cavalier fashion. I hit compute, and I get the lower limit and upper limit, and all I have to do is round them. So 3 decimal places, that's 98.111. My upper limit is 98.489 after I've rounded it. And they think I've done this right. So here's the deal. When I was a kid, I was taught that 98.6 is the ordinary, the healthy body temperature for a person. And here we just found that of these 103, and 103 is a lot, we think that the true mean of the population, and if they're randomly selected, they should be representative of all healthy adult humans, goes from 98.1 to 98.4. Well, 98.6 does not fall in that interval. So it appears that the mean body temperature is lower right there than 98.6. There you go. Here's a very interesting problem, one of my favorites because it allows me to talk about history just a little bit. We're in chapter 7, section 2, so we are working on confidence intervals to estimate population means. And here what we have is mercury in fish. And mercury poisoning is a very damaging thing that affects a person neurologically, which is never ever good. This has been known for a long time. There was a famous mathematician, you may have heard of him, in 1865, who wrote a book in which he described a person who was probably undergoing some of the symptoms of mercury poisoning. The person in 1865 was a mathematician named Charles Lutwidge Dodgson. And when I say you've heard of him, you're thinking, no, I've never heard of a guy named Charles Lutwidge Dodgson. He wrote under a pen name. The Charles he turned into Carroll, and the Lutwidge, which is the German version of Lewis, he changed into Lewis. He changed the order and wrote under the name Lewis Carroll. The book was Alice in Wonderland, and he described a hatter. Hatters often used mercury in curing felts to make hats, and the mercury fumes typically poisoned them and made them mad as a hatter, which is an expression that predates Carroll. He didn't invent that phrase. He never even calls the hatter mad. He just describes the guy, and it's like he's crazy. So the Mad Hatter probably suffered from mercury poisoning. Anyway, what we're trying to do here is look at these parts per million of mercury in some sushi at various stores in a major city. And they want a 99% confidence interval for the mean amount of mercury. And notice that 1 part per million is the safe level. That's the maximum, and we're already over that. So this is an interesting problem because it requires us to key in the values or just use them in StatCrunch. So here we go. Open these data in StatCrunch. Go to Stat. We're doing a mean. Do we want a Z or a T? This is always the question. If you go back to page 236 in the textbook, then you have a little table here, and it tells you if sigma is not known. Do we know sigma? I don't see sigma here. There's no sigma at all. We do not know sigma, and so as typical, we use student's T distribution. So back to StatCrunch, stat T stats, 1 sample. I do have the data this time. Nice. So all I have to do is choose the column where that data resides, enter my 0.99 for my confidence interval, and I'm done pretty much. It does all the work for me. It counts the number of data items. There were 7, and subtracts 1 to get me my degrees of freedom of 6. Gives me my lower limit and upper limit. Really all I have to do is the rounding. So this turns into 0.180. And the upper limit turns into 1.249. I seem to have done that correctly. So is there too much mercury in tuna sushi? Be a little careful. It looks like there are 2 choices, and of course scrolling reveals that there are actually 4 choices. We already noticed that one of these is too big to be healthy. 1.25 is too much. And we've just found that it's possible, not necessarily guaranteed, but it's possible that mu could be greater than 1, which is the safe limit. So it is possible that the mean is not greater. No, that doesn't make sense. Yes, because it is possible that the mean is greater. Also, at least one of the samples does exceed the safe level of 1 part per million. So at least some of the sushi, it already has too much.